好了，那有那个回来了哈，那我们就准备开始喽。Alright, so upon pick a question. We want to challenge problem number 11, string exercises. 11. 11. We want to challenge problem number 11, string exercises. We reject. Alright, reject. Another question? I will. So we would like to challenge problem number 6, building process. Number 6. So we have 1, 2, 3, 4. We have 10 more questions. We would like to challenge problem number 3, Lato.
We would like to accept.
Alright. I mean,
I'm the reporter from Team Verify. Now I'm going to report problem number 3, The first is a problem statement. Attach a ball to each end of the string and connect the center of the string to a pivot. When the pivot oscillates along the vertical direction, the ball starts to collide and oscillate with increasing amplitude. Investigate the phenomenon. So the key questions will be on what parameters affect the oscillation of the ball and how to describe the motion of the increasing phenomenon. My presentation will be in this order. First of all, I'm going to talk about the preliminary observation, and it's my experimental setup. And then I'll talk about the experiment and theory of steady state and increasing state. And the last part is the conclusion. First, let's see the phenomenon. You can see that when our hand is up and down, and it will have the increasing with the amplitude of the lato will increase. So the amplitude will increase and get to the steady state. And then it's our experimental setup. This is we use a motor and to get the driven force, and then so the driven force can be approximated to F equals to sine omega t, which omega is the frequency of the motor. And then is the lato is the string is put under the setup. And then is our theoretical is theory expectations and results of steady state. First, from the energy, we assume that it is a pendulum. The lato is 2 pendulums. So when the lato is from the biggest theta to when it collides, it has energy conservation, and it can be right at that. And so we can get and by integrating it, we can get the period of the lato, and then we define T as the 1 over its natural frequency. And then is the periods to different lengths. We can see that when it comes to steady state amplitude, when the period of it the amplitude of it isn't affected by its length. That is the maximum angle of different latos are similar because of our theory. And then is our the experiment that the period to the square root of the length, and we can see that it's linear. So the motor's acceleration isn't very profoundly according to different, and we also observe that the motor's acceleration doesn't vary profoundly according to the different rotation speed, and that from these graphs we can see T is proportional to the square root of L. And that is our theory and experiments of increasing amplitude. First is the theory expectation. Because if we consider the damping motion, of the lato, the motion equation of it can be written like this, and notice that the lato will only oscillating with increasing amplitude when the the frequency of motor, that is omega, is same as the Laplace's natural frequency, that is the pendulum's natural frequency, which is omega 0. And we can have the solution of it as damping model. And why do we use damping model to on our theory? Because the energy loss due to damping is the main factor is the force collision. Because it's an elastic collide, so the coefficient of it so we can calculate the inelastic collide coefficient of it, and we can get that the total energy loss is proportional to the speed when they collide. So that is the same model as the damping. So we use damping model to do it. So this is the collide term. So the first experiment we do with this is the slope function of amplitude that in damping model, the amplitude of Laplace will decrease as exponential, like this. So we can calculate it. And results of amplitude slope is this is the time vs the max amplitude during the motion. That is, we can see that the Laplace the amplitude of it will increase and it will get to a steady state in the when the frequency of motor is the natural frequency of it. And we can see that exponential curve fitting is accurate, and deviation only happens to the value, not the trend of the oscillating motion. So we can know that it's exponential. So, and also the linear fitting is also accurate when the period is small, and when we just see at like first 4 seconds, and the damping effect is so we think that the damping effect is not big at here, and also the slope has positive relation to length. And that is our result of the slope of amplitude. That is, what is the slope of amplitude? Like we use the first 2 seconds or 4 seconds to get the slope because it can be approximate to linear. So and then use it, we can get it is proportional to square root of L. And then is our conclusion. We know that the maximum angle is approximately the same to various the length of Laplace, and the motor's acceleration doesn't vary accordingly to different rotation speed. And then for the steady state phenomenon investigation, we can see that it can be seen as a large angle pendulum, and also the period is proportional to a square root of length. Also, the increasing state of it can be modeled on a resonance system, and the damping effect is not significant at the beginning of the oscillation and can be approximated using derivation. That is our thank you.
Alright, so what's the definition of the amplitude you mentioned in the
our definition is that when theta is getting the biggest, just like
the amplitude is the theta or the L times the sine theta.
Theta.
Yeah, okay. Can you turn to page 5? So on the first graph you're showing, so there's a small gap in the beginning, so there's a small perturbation is needed to start the motion.
What? Can you please clarify?
Does the small perturbation required to start the lateral motion?
Small
Perturbation,
what is
like an initial angle.
the small no.
No. And then to page 8. So the frequency equation you're using here is the small angle formula. So I just done the correction for the bigger angle.
I think it's big angle. I think.
Okay. So how do you define the period in lateral motion since it's not like a usual pendulum system?
Because the big and it also have the steady state, so we can define the period.
Okay, from page 11. So what do you mean by if the modal phase is natural frequency?
Because it's the
Okay, that's all my question. here's the problem statement. And the main focuses of the proposal is how the relevant parameters affect the oscillation condition, and also the motion description of the increasing amplitude. And here's their overview of their presentation. So in theory part, they use energy conservation when the oscillation is steady, and also the equation of motion to describe how the lateral motion, and also the amplitude function, and lastly the coefficient of restitution. And in their experiment parts, they discussed about how the period, the ratio between the period and the length of the string, and also the amplitude against the different lengths. And lastly, they have the maximum amplitude against different length of the string. And their parameters would be the length of the string and the angular velocity. And their conclusion would be the maximum angle is approximately the same. And also, it can be seen as a lateral can be seen as a large angle pendular motion. And lastly, increasing states can be modeled on a resonance system. And here's the pros and cons, I think, for the reporter. And for the pros, I think they have clear theory explanation, and also they have comprehensible comparison between their theory and their experiment data. And also they have precise conclusion. But our suggestion would be they can give more on the observation. And also they have inadequate variable, which is 2. And also the lack of data elaboration, which means that they don't have much discussion on the data. And also, and that's all. And here's the point I would like to discuss with the proposal. So in the theory part, they mentioned the damping effect is negligible, and I would like to know the reason why. And also the collision conditions, how the collision condition was considered in their theory model. And lastly, I want to talk about the stack condition. And for the experiment part, I have some confusion about their data analysis method, and also the rotation speed he mentioned in his setup. So I would like to invite the proposal. So first of all, can you turn page through the setup? So can you explain how the motor works right here?
How the motor works? There's a motor and this is the motor, and things are put like this, and there's things to restrict these things to vertex. And then when the motor, I think I and then when the motor spins, the motion of the laterals here can be similar to this.
Yes. So what do you mean by the rotation speed of the motor? Since the lateral motion requires oscillation on the pivots, right?
Yes.
So the rotation speed should be keep changing from both clockwise and anti-clockwise.
Yeah. No. It can just like when it's spin like this, it goes up and goes down, and because in this direction it is simple harmonic, so it can.
Yeah, I mean, so is the motor always turning clockwise or anti-clockwise?
Yes, the frequency of the motor is constant.
Then what do you mean by the rotation speed of the motor?
Just rotations.
Oh, okay, I get it. And next, can you turn to your theory data in the board graph, page 14. Okay, so right here you mentioned that the damping effect is negligible. So you firstly give an explanation on how the damping effect works and also the reason why it is negligible.
Okay. Come to the we said that the energy loss is proportional to this thing. So we think that proportional to v. So proportional to v squared. So we think that it also means that so we think that it can be at the damping model. Like this, because the force the energy loss can be written as like something times v squared. So the equation can be written as the damping model.
You see that the energy loss is something times v squared.
Yes.
Okay, can you turn back to page 14? Can you explain the damping effect right here? And so the photograph shows right here, three of them is exponential and the one on the right is linear. Can you explain the difference?
It's not linear. It's not really linear. Oh, I think it's a little bit linear, but I think it's because the time we capture is small, so it seems linear.
Yeah, I mean also,
If I capture it longer, it will be exponential.
Okay, so can you explain why within 8 seconds of oscillation, since also you mean the critical value of whether the damping effects or not? What the critical value of whether damping effect can be negligible?
We said that if the capture of time is small, then t is small, so the damping effect, so the damping effect can be I use the variable because from the damping effect model we can get and when t is small enough, and this is similar to 1, so it will be like just simple harmonic, which means that f total f equals to plus kx, and no damping term.
And what does the x you're seeing right here?
It's I think I should write, but it's okay. Just
so it's the angle of the lateral motion.
yes.
Okay, so can we move back? So I feel like you have a very good point, but what I mean is that so as the lateral motion begins, it begins from small angle, right?
Yes.
So from small angle, the damping effect should be relatively large rather than when it's big angle. Then why would damping effects is negligible within the first 8 seconds of oscillation?
Because t is.
Yeah, I mean,
I think no, not 8 seconds, because I think we wrote it wrong. Maybe it should be shorter.
Yeah, I mean, so at the beginning, the oscillation angle of lato is pretty small, right?
Yes.
Yes, that means it has small energy, small potential energy, right?
Yes.
So the damping effect will be larger, relatively larger than the condition when the pendulum has big angle motion.
Why it will be it will be larger?
Yeah, since you have small energy, if your angle is small.
But the velocity is also small.
Yeah, so the swing angle is small. So that means when you reach its maximum swing angle, the potential energy it has is smaller than when it can reach larger angle, which is after 8 seconds.
So you think that the damping effect should not be negligible in the first?
Yeah, if you want to say that the damping effect is negligible, it should not be at the first 8 seconds, since the amplitude is getting bigger.
I think it's small when comparing to the whole motion, but yes, I think it will not be negligible. No, I think it will be negligible.
Okay.
Yeah, because small velocity.
Okay. And so when you say maximum angle, what do you mean by maximum angle? Is it the stable maximum angle?
What is the same all that?
Yeah. So from the process to reach stability, it can be very precisely, since sometimes the swing angle can be larger than the value it should stop at. Right?
Yes.
Yes. But after the correction of the system itself, it should reach a stable angle.
Yes.
Then so is the maximum angle you're saying is the stable angle, or the overall process, the big one?
Maximum angle should be just the amplitude. So it will so I think the period no, I think the maximum angle will change during the oscillation.
So the maximum angle will change
During the oscillation.
Okay.
And it will reach the steady state if the frequency of driven force is the natural frequency of.
Okay. Can you turn to page 9?
Page 9.
Yeah. So you stated that the graph on the right side could be concluded to a linear.
Right side.
Yeah, like on the right side. Sorry.
Yeah.
And then it can be concluded to a linear. Can you explain why from your theory class?
Because T is 2. Because the pendulum theory that T is 2. Something times 2 with
Right.
square.
So in our discussion, we firstly talked about the experiment setup that the reporter has used in the experiment, which is the motor. And secondly, we talked about the damping effect. The reporter thinks that the damping effect can be negligible in the first 8 seconds, but the opponent thinks that in the first 8 seconds, the initial energy is small. So the damping effect should relatively be larger. So if you want to say that it is negligible, it shouldn't be at the first 8 seconds. It should be after a critical value of time. And lastly, we talk about the maximum angle. The reporter didn't clarify in his presentation. So the maximum angle he was saying is that the maximum angle will change as time passed in the experiment. And that's all my presentation.
Okay, so Well, the max angle goes into a constant after a long period of time in the stable state.
It will reach a stable oscillation angle. The amplitude would be, yes.
Then how about considering the ball is an only system? Well, what force will do work to the ball, or only
The oscillation on the pillars.
how about the strings? What strings do work to the ball?
So I believe that the string will do some positive work to the whole system, but since the string might slack or something that leads to energy loss, so it might do some negative effects to the system.
And so you mean strings will do some kind of negative work to the ball?
Yeah.
Then consider about the stable state. Well, I mentioned that in long term and long period of time, after long period of time, the maximum angle will be stable. So this means the energy is like a constant.
Yeah.
Then considering the energy loss, why would it still be a constant? So it means that if we consider energy loss, then there's some energy source. There's still some energy sources doing force or doing work to this system.
During what?
Work.
There are some energy what?
Source.
Source. Yes.
You can consider that an object like strings or something like that is keep doing
Yeah, the
positive work.
string is doing positive works. So
So you mean string. Then why? Because we all know that the velocity of the ball is virtual to the string's direction, right?
yes.
Then how do this work?
Because it will up down up down.
Oh, so you mean it is not totally virtual?
Yes.
Okay. Then, well, that's all of my questions. behavior of that phenomenon. And they use increasing amplitude to describe the energy condition in this system. And also they use ball collision to count the damping motion. And some predict has based to the theory and the comparison to their data. And yes. And in their conclusion, they use resonance to account for the steady state over time. And linear feeding graph is accurate within a small time period, as they have said. And well, this is our viewpoint for the recruiter. The advantage is that they describe the phenomenon and the theoretical model very clearly. And the second suggestion is that the speaking could be more thoroughly. And also, sometimes using a formula to give out some product, maybe you can mention what's the formula name or what's the formula's base on. Yes, and that would be better. And the reported lacks of data evaluation. And this is the remarks to the opponent. Their confidence is the advantage. And also the suggestion is sometimes they're interrupting the reporter's explaining. In the discussion, they discuss the equipment set up for the motor, and the reviewer agree with the opinion of using the clockwise or the opposite side to modify and to model the hand's behavior. And they have also mentioned the damping motion in the model. And the reviewer agreed with the opinion that because of constant energy loss. And about the maximum angle, it is a stable condition after a long-term period. And for the critical parameter that would make the damping effect in this situation, the reviewer agreed with the state that damping effect cause energy loss decrease. There are some missing points for the T. The period time is linear to square L, as have mentioned in the report, but didn't explain more. The reviewer is curious about that. And for that's all.
Finally,
Okay, and that is my concluding remark. In my presentation of our own report, we said that the steady state can be seen as a large angle pendulum, and the period is proportional to square root of length. And in increasing state, we said that the increasing state can be modeled as a resonant system, and damping effect is not significant at the beginning of the oscillations and can be approximate using the linear relation. And then, for a short question, the opponent asked about what is the definition of amplitude, and I answered the maximum angle. And what does the initial angle is required to study? Does initial angle is required to be small angle to start motion? And I answered no. And how I have done the correction of big angle for and however. Oh yeah, and I used the big angle formula. And how do I define the Laplace system here? I said that I define as the like pendulum. And what's the meaning of the motor speech, the natural frequency? It's just in that here. And damping effect is negligible because it's proportional to V squared, so it can be written as damping model format. All our graph is exponential, not linear, but it seems linear at first, and we think that damping effect is not relative larger and smaller angle. But because due to our experiment, and then the V is smaller at initial, and we use the same frequency for motor, and we all use constant frequency of motor and define the.
All right, so we got 5 minutes from jury. Question on 3, please.
This is your correct large angle formula. What's the effect of large angle?
What the
The thing, the large they swing and large angle.
and what do you?
So what the equation you're using is small, good for small angle entering only. It's not good for large angle. So what correction do you make?
Okay, maybe I have some here. But I think I use the I use the energy conservation. It can be used in large angle form.
I agree with the reporter using energy condition to describe this term. And also, I know that the difference between small angle, the small angle can be similar to simple harmonic. That is not exactly what the big angle behavior is. That's what I know.
So I think so the reporter is using the small angle equation, and to correct it, large equation, which is some like Taylor or something like that, should be applied to, and also the condition with the smaller maximum amplitude should be separated from the condition with larger maximum amplitude.
I think Taylor is only used to see that the amplitude is almost the same in different. The amplitude in Taylor is also only used to describe that the amplitude is almost the same in different length of
Right. Any further question from jury? Another?
So have you checked your resonance frequency with your theory?
what do you mean?
Compare the experimental frequency.
What?
You explain the thing as resonance. So the frequency you observe in the experiment, does it match the theory you did?
Yes.
Do you have data?
What do you mean?
Do you have the data?
Data? I think no, but the increasing amplitude will only happen in our observation set that when the motor frequency is natural frequency of the
All right. So I think we can start to do the grading. For the score. So for the, we should have another grade for the reporter. All right. All right. All right. 7, 6, 8, 4, 7. Now next, the score for the component. All right, 7, 7, 7, 5, 8. And finally, the score for the reviewer. Ready? 6, 7, 6, 5, 5. All right, finish the stage.